Okay. Um, Thank you very much and welcome to College Algebra. Today we would be discussing section 2.5, which talks about transformation of functions. All right, so there are some graphs of common functions that we have to get ourselves familiar with. Graphs of common functions. We have to get ourselves familiar with. The first one is the identity function. And the identity function is given by f of x is equal to x. Its domain is over all real numbers. Its domain is from minus infinity to positive infinity. Its range is also minus infinity to positive infinity. And if we visualize it, it looks it's a straight line through the origin. So this is the graph of y is equal to f of x, or y is equal to x. F of x is equal to x, so y is equal to x. And we can see that it's increasing throughout. So it's increasing in the domain. So it's increasing on from minus infinity to positive infinity. And it's also an odd function. Okay. The next on the list is the quadratic function. The next is the quadratic function. So generically, the quadratic function of, let's say, y is equal to x squared looks something like this. So the graph of y is equal to x squared. The generic quadratic function looks like this. Its domain is from minus infinity to infinity. Its domain is over all real numbers. Its range, you can see the lowest point it gets to is this point here, which is 0. So its range is from 0. So its range is from 0. You can see the lowest point is from here, and it goes all the way up. So its range is from 0 to infinity. And it's decreasing. You can see that on the left side, it's decreasing here, and on the right side, it's increasing here. So it's decreasing on the negative axis. So it's decreasing from minus infinity to 0, and it's increasing from 0 to infinity. Um, and it's an even function because of the power 2, f of x is equal to also f of minus x. So that makes it an even function. Okay, let's look at some more. The next on the list is the square root function. This is the square root function. The square root function is the generic square root function is given by a graph of y is equal to the square root of x. And its domain, you can see it only goes from the positive axis. So its domain, you can see it's only going starting from 0 and going to the positive axis. And its range also starting from 0 and going up here. So domain is from 0 to positive infinity. Its range is also the same from 0 to positive infinity. You can see it's increasing on 0 to infinity. You can see that it's increasing. So it's going up all the way up here. From 0, you can see that this function is a function that is increasing, is going up. So it's increasing from 0 to infinity. And it's neither an even nor an odd function. Neither even nor odd. Okay, so this is the square root function. Let's look at another one, which is the standard cubic function. The standard cubic function, its domain is, all right, so before let's first graph it. So the standard cubic function looks like this: y is equal to x cubed. It looks like it. This is domain is all real numbers from minus infinity to infinity. Its range is also from minus infinity to infinity. It's increasing on. It's increasing on. It's also increasing throughout, right? From minus infinity to infinity, it's increasing, and it's an odd function. Okay. Let's look at the cube root function also. Let's look at the cube root function. Um, so for the cube root function, let's try to graph it. It looks something like this. So this is y supposed to the square root of cubic root of x is equal to. And its domain is from minus infinity to infinity. H range is also from minus infinity. It's increasing on. It's increasing from minus infinity also to positive infinity. Okay, and it's also is an odd function. Okay. All right, so now that we know the different forms of some of the most common standard functions, we're going to begin looking at how we can transform some of these functions. So the first is the vertical shift. So if we say, well, we let f be any function, let f be a function. Let f be a function and c a positive real number. And c a positive real number, then we say when we have a transformation y is equal to f of x plus c, we say the function is shifted c units vertically upward. All right, and y is equal to f of x minus c. Is shifted c units vertically downward. C units vertically downward. All right, so let's use an example to explain. So example one. And it says use the graph of f of x is equal to absolute value of x to obtain the graph g of x is equal to absolute value of x plus 3. All right, so let's see how we do this. So the original absolute value of x looks like this. So this is f of x, or y is equal to absolute value of x. And so to get a graph of y is equal to absolute value of x plus 3, we have to shift the graph 3 units upward. It's a vertical shift of 3 units upward. So suppose this is 1, this is 2, and this is 3. So now we'll have the same graph that is shifted 3 units upward. So it will look something. No, let me use a different marker. So it will now look like this. So this will be the graph of y is equal to absolute value of x plus 3. It's a vertical shift upward of 3 units. Okay. All right, so let's look at horizontal shifts. Again, if f is a function and c is a positive real number, then y equals to f of x plus c is the graph of y is equal to f of x shifted to the left. Shifted to the left c units. And y is equal to f x minus c. X minus c is also the graph of f of x shifted c units to the right. C units to the right. All right, so let's look at an example. Should be our example 2, and it says use the graph of f of x is equal to the square root of x to obtain the graph of f of x is equal to the square root of x minus 4. All right, so square root of x minus 4 looks like a graph that is shifted 4 units to the right, or shifted horizontal shift of 4 to the right. So if the original function of a square root, if this is the graph of y is equal to the square root of x, the square root of x minus 4, the square root of x minus 4 will be a shift of 4 units to the right. So it will be a graph that looks like this. So this will be a graph of y is equal to x minus 4. A horizontal shift of 4 units to the right. Okay, let's look at reflections, the different kind of transformations that involve reflecting along the x-axis or the y-axis. So the reflections. Reflections of graphs. Oh, all right. So reflection about the x-axis. So reflection above the x-axis is given by y is equal to minus f of x. So it means the x values are negated. Wherever x is, we make it negative f of x. So y is equal to minus f of x is the graph of y is equal to f of x. Is the graph of y is equal to f of x. All right. Is the graph of f of x reflected about the x-axis? So reflection about the x-axis means if a graph f of x is on this side, it will reflect it across the x-axis is going to be on this side now minus f of x. If it's on this side and it's reflected across the x-axis, then it's going to be on this side. Okay, so that's a reflection across the x-axis, along the x-axis. All right, let's look at also the reflection across the y-axis. Let's look at also the reflection about the y-axis. So reflection about the y-axis. Let's look at it on the next page. So reflection about the y-axis. Okay. So the graph of y is equal to f of minus x is the graph of y is equal to f of x reflected about the y-axis. Reflected about the y-axis. So let's use an example to illustrate this. All right, so before that, let me also quickly show, so the graph of, if we reflect a graph along the x-axis, if it is here and it's reflected along the x-axis, then it comes here. So if this is f of x, if this is f of x, then this becomes f of minus x. This becomes f of minus x. Okay. Or if it is here, And then it's going to come here. All right. So that is reflection along the y-axis. All right, so let's look at the next. Let's look at an example. So this should be our third example. It says use the graph of use the graph of use the graph of cube root of x to obtain the graph of the cube root of negative x. All right. So the cube root of x, earlier we saw that the cube root of x looks something like this. This is y is equal to the cube root of x. So if we reflect it along the y-axis, it's going to look like this part here is now going to look like something like this. And this part down here is also going to look something like this. So this will be h of x is equal to the cube root of negative x, whereas this would be f of x. So this is a reflection across the y-axis. Okay, let's look at vertical stretching and horizontal and vertical shrinking. So vertical stretching, vertical stretching and shrinking graphs. Vertical stretching and shrinking graphs. So we say let f still be a function and see a positive real number. Then if c is greater than 1, and the graph of y is equal to c multiplied by f of x is the graph of y is equal to f of x vertically stretched by by multiplying each y coordinate. By multiplying each y coordinate by c. And if c is between 0 and 1, then the graph of y equals to cf of x, c multiplied by f of x is the graph of y is equal to f of x is the graph of y is equal to f of x vertically shrunk by multiplying each of the y coordinates. It's shown by multiplying each of the y coordinates by c. All right, so let's use some example to illustrate one of this. This will be our fourth example, so example 4. So it says use the graph, of f of x is equal to absolute value of x to obtain the graph of f of x is equal to 2 times absolute value of x. All right, so if we have the original absolute value function f of x, we want the graph of g of x, which is 2 times absolute value of x. So 2 is greater than 1. So that means we have a case of a vertical stretching. So we will be stretching the function by 2 units. So let's look at the original function. Original function is f of x, which is so this is f of x is equal to absolute value of x, and the g of x will be a vertical stretching. So g of x will be stretched 2 units up. So this would be g of x equal to 2 times absolute value of x. This would be a vertical stretch because 2 is greater than 1. If 2 were less than 1, then it would have been a vertical shrink. All right, so let's look at horizontal stretching and shrinking of graphs. So horizontal stretching. Stretching and shrinking graphs. Okay, so we say let f be a function. Let f be a function and c a positive real number. And c a positive real number. If c is greater than 1, the graph of y is equal to f of c of x is the graph of y is equal to f of x horizontally shrunk. Horizontally shrunk by dividing each of its x coordinates. So its x coordinates by c. And if c is between 0 and 1, the graph of y is equal to f c times x is the graph of f of x. So graph of y is equal to f of x horizontally stretched. Horizontally stretched by dividing each x coordinate by c. All right, let's use an example to illustrate the horizontal stretching and shrinking. So this will be our fifth example. So this is example 5. So it says use the graph of f of x equal to x squared to obtain the graph of g of x. And the graph of g of x is equal to half x squared. All right, so the original graph f of x is equal to x squared looks like this. So this is f of x is equal to x squared. So half is between 0 to 1. And so this will be a horizontal stretching. We said if we have C, which is a positive real number between 0 and 1, then the graph of y is equal to f of C times x is horizontally stretched by dividing each x coordinates by C. So if we divide by C, that means the x coordinates are going to increase. So we have a graph that stretches horizontally. So this is going to be something like a graph that looks something like this. So this will be the graph of g of x is equal to half x all squared. It will be a horizontal stretching. All right, so let's look at some other examples. So let's look at example 6. So example 6, that involves multiple transformations. So example 6, it says f of x is equal to, use the graph of f of x is equal to x squared to obtain the graph of h of x, which is equal to 2 times x minus 1 squared plus 3. Okay, so let's start with the original graph. So the original graph, f of x is equal to x squared. So this is the graph of y is equal to x squared. And so x minus 1 squared is a shift to the right by 1 unit. So instead of starting from 0, instead of starting from 0, it's not going to start from 1. So this is the graph of y is equal to x minus 1 squared, which is a shift 1 unit to the right. Just a horizontal shift 1 unit to the right. So shift of 1 unit to the right. So it's a shift of 1 unit to the right. So we get this. And the next one is it's being multiplied by 2. So the next one is being multiplied by 2. So that is so it's being multiplied by 2. So that is a vertical, because 2 is greater than 1. That will be a horizontal shrinking. Because 2 is less than 1, that will be a horizontal shrinking by 2 units. So that will be dividing the x coordinates by 2 units. So let's try to do that. So we say horizontal stretching and shrinking. If C is greater than 1, if we say vertical stretching, and we talked about vertical stretching and vertical shrinking earlier, we said if C is greater than 1, then the graph of Y is equal to 2 times f of C. It's a vertical, if C is greater than 1, then it's a vertical stretch. It's vertically stretched. And if C is between 0 and 1, then it's a horizontal, shrinking. So C is greater than 1 here. So this is a vertical stretch. So this function is still shifted to the right by 1, but now it's stretched upwards. So this is Y is equal to 2 times x minus 1 squared. And finally, it is shifted upward by 3 units. So it's a vertical shift. It's a vertically shifted upwards by 3 units. So let's look at that. So it's a vertical shift upwards by 3 units. So now, finally, it becomes, this is 1, 2, and this is 1, 2, this is 3. So now, instead of it's vertically stretched, it's vertically shifted upwards by 3 units. So now it becomes, all right, so this is the final graph, h of x, which is equal to 2 times x minus 1 squared plus x minus 1 squared plus 3. So this should be the final form. So let's look at one more example that involves multiple transformations. So this will be our example 7. And it says given f of x is equal to the square root of x, obtain the graph of h of x is equal to the square root of minus x plus 2. All right, so originally the square root of x, y is equal to square root of x. This is y is equal to the square root of x. And so if we add 2 to it, that means it's been shifted to the left by 2. It's shifted to the left by 2. And if the x becomes negative x, that's also a reflection. If the x becomes negative x, we can see that it's a reflection about the y-axis. So we said reflection about the x-axis, y becomes negative f of x. So the y value becomes negative. The positive y values become negative y values. And for reflection along the y-axis, the positive x values become negative is reversed. Okay. So this is y is equal to let's look at y is equal to the square root of x plus 2, which will be a shift to the left by 2 points. So if this is 0, so this should be the graph of y is equal to the square root of x plus 2. And reflected across the y-axis, it becomes and so reflected across the y-axis, it becomes this. So this becomes y is equal to the square root of negative x plus 2. All right, so this brings us to the end for our discussion on transformational functions on session 2.5. So we'll see you in the next video.